Thanks very much. So here a talk based on work which I've been doing with a bunch of people, namely over the past years, namely Pedro Niceto, Cristina Câmara, Thomas Bohaupt, Sareshna Puri, and Marti Rosselló. And in a nutshell, this is about solving nonlinear PDEs in gravity, in integrable systems in gravity, but not through usual techniques of nonlinear PDEs, but rather through matrix factorization techniques in conjunction with complex analytic methods. So the theories we'll be looking at are going to be gravity or supergravity theories in dimensions 4 or higher at the two-derivative level and in Lorentzian signature. And these are typically theories that comprise gravity, Maxwell fields, and neutral scalar fields. There will be no cosmological constant in the game. There will be no potential for these neutral scalar fields. Now, it's, of course, very well known that the associated field equations, the field equations in these theories are nonlinear PDEs, and therefore it's complicated to, it's complicated to study their solution space. So it's a non-trivial endeavor to actually obtain exact solutions to these field equations. Now, to proceed in trying to analyze the solution space, what we'll be doing in this talk is we'll be restricting to a subspace of solutions that only depend on two coordinates. And these coordinates, I'm going to denote them by rho and v. Rho will be taking positive values, v will be taking values in R. So what this means is that we'll be looking at solutions to these field equations that arise by solving nonlinear PDEs in two dimensions. Now, it's well known how to actually obtain these nonlinear PDEs in two dimensions. This is done by dimensional reduction. So we start, say, in d dimensions, d bigger or equals to 4. We then go down to two dimensions, but we do the reduction in a two-step procedure. And this two-step procedure is called the Ehlers reduction. So in the first step, one reduces from d dimensions all the way down to 3 dimensions, of course, assuming that there are a number of commuting isometries in the game. Once one is in 3 dimensions, since one started with Maxwell fields, and also since one is performing a Kaluza-Klein reduction, one ends up with with a bunch of fields in 3 dimensions that include Maxwell fields. You are then instructed to Hodge dualize these Maxwell fields, these two-form fields, into scalars, so that at the end of the day, once you have done this dualization, you have a 3-dimensional model comprising gravity and just scalar fields. Now, these scalar fields will take their values in some nonlinear sigma model, and for the purpose of this talk, we'll be assuming that the nonlinear sigma model is the one based on a symmetric space, based on the linear G here. So we'll be dealing with symmetric spaces G mod H coupled to gravity. So that's the theory in 3 dimensions, which you get by Kaluza-Klein reducing the theory in d dimensions down to 3 and Hodge dualizing the Maxwell fields. And then finally, in the second step, you go down to 2 dimensions, assuming that you have another isometry. And so what you then get in 2 dimensions is a theory of gravity with scalar fields coupled to it. And this theory is well known to be classically integrable. Now, what does it mean that the theory is classically integrable? It means the following, and I'll explain these words later in more detail. It means that there is a linear system or a Lax pair associated to these 2-dimensional nonlinear PDEs, which you are trying to solve. I'll explain later what I mean by a Lax pair in the linear system. And there are typically 2 linear systems in the game. One, which is called the Belinsky-Zakharov linear system, and the other one, which is called the Brighton-Lunder-Mason linear system. Now, the first one is perhaps the one that is more widely used. It's the one that arises not just in this gravitational context, but also if you look at, say, nonlinear PDEs, such as KDD equations. The Belinsky-Zakharov linear system is the one that is often used when attempting to construct solitonic solutions to nonlinear partial differential equations. The other one, the Riemann-Hilbert linear system, that is, well, I guess it's fair to say that this is a lax pair or a linear system that is less used. It was originally introduced by Riemann and Mason in 1987. It was then further studied by Nicolai in the early 90s, and also by Perry, Liu, and Pope in 2007. And then it lay dormant for a while until interest in this linear system was rekindled in papers by Katsimpuri, Kleinschmidt, and Vermani, and then we also went ahead and worked on it.
Can you say a bit more what the interest was again?
Right, I'll come to that in a second. So there are these two linear systems, and they turn out to be equivalent. So they are equivalent, but the methods which you use to solve them are very different. And that will now address your question. So the first one, the Belinsky-Zakharov one, as I said, is one which is used to construct solitonic solutions to nonlinear partial differential equations. And this is done through a method that is called the dressing method. You start from a given solution, a seed solution, and then you try to construct, a solitonic solution, and then you try to generate new solitonic solutions by dressing the seed solution. And this means that there is going to be a dressing matrix in the game. And in this context of constructing solitonic solutions, this dressing matrix is usually is taken to be a rational matrix with simple poles. Now, this is not the purpose of my talk, so I'm not going to go any further into the Belinsky-Zakharov approach, linear system approach. But let me then contrast this with the Breit-Muller-Mason approach, which is an approach which does not need seed solutions. In this approach, one is not restricted to rational matrices with simple poles. And as I told you before, if you recall what I told you about the systems one is studying in 3 or in 2 dimensions, these are scalar fields whose target space is a symmetric space. So there is a Lie group G involved in the game. Associated to this target space, there is an involution. And this involution here is a central quantity in this Breit-Muller-Mason approach. So what this linear system does is, what the Breit-Muller-Mason linear system does is, it uses group theoretical or Lie algebra ingredients that are encoded in this Cosset space, G mod H. So this to contrast the Breit-Muller-Mason linear system approach with the Belinsky-Zakharov approach. And what we'll be seeing in this talk is that I have not yet told you what this linear system looks like and what it is, but what we'll be seeing is that we can actually study this Breit-Muller-Mason linear system by matrix factorization theory, and this matrix factorization theory is called Wiener-Hopf matrix factorization theory. And so I will now in the following try to explain all these words. But before I do so, still a few more comments here on the Breit-Muller-Mason linear system. This linear system will depend, or will use a spectral parameter, which is here denoted by tau and takes values in the complex plane. The Breit-Muller linear Mason system, as I said, will be solved by Wiener-Hopf factorization of monodromy matrices, and this factorization has to be done with respect to a contour. So it doesn't make any sense to talk about factorization of monodromy matrices without specifying the contour. Now it will turn out that this factorization, that this Wiener-Hopf factorization technique, is equivalent to solving Riemann-Hilbert problems in this complex tau plane. So there will be Riemann-Hilbert problems appearing in this game. And finally, since the factorization has to be done with respect to a contour which you choose, you may be in a situation where there are several contours from which you may choose, and depending on the choice of the contour, you'll be actually getting different solutions to the field equations, all coming out of one and the same monodromy matrix. So these are a few highlights which I'll try to explain in the following. But before I do that, so I told you initially that the theories we are going to look at are theories without a cosmological constant or without potentials for the scalar fields. So now you may ask, what happens? I also told you that the subspace of solutions we are looking at, which is a subspace where the solutions effectively only depend on two coordinates. It's, as I said, it's well known that this subspace is integrable. It has an integrable system associated to it. So you may wonder what happens when one turns on a cosmological constant or a potential for the scalar fields. Is the system still going to be integrable? You could also envision, I told you that we are also going to restrict our analysis to a two-derivative Lagrangian. You may also ask what happens if there are higher derivatives involved in the game. Is there going to be integrability in the presence of higher derivative terms? So you can look at turning on a cosmological constant or turning on the potential for the scalar fields or turning on higher derivative terms. You can look at it as introducing deformations of your original Lagrangian. And the question is whether there are deformations that preserve integrability. Now, this is a hard question to answer. And in this context, you may ask whether machine learning can actually help you in identifying such integrable deformations. And this will, well, some of this you will see in the workshop talk here by Damian. He will tell you about integrability in the presence of cosmological constants and potentials for these neutral scalar fields in conjunction with machine learning. Right. So now let me explain all these words which I introduced. So we start in d dimensions, d bigger than 4. And as I said, we are going to look at the solution space where characterized by the fact that the solutions only depend on two coordinates. So a dimensional reduced down to 2 dimensions, and we do this as a two-step procedure. So first we go down to 3 dimensions. Now, in 3 dimensions, as I said, you will have Maxwell fields around, so you dualize them into scalars. So after having done that, you now have a gravitational theory with scalar fields coupled to them only. And we'll be assuming that these scalar fields take their values in a symmetric space. G mod H, where G is a Lie group, and H some maximally compact subgroup. And these various scalar fields can be arranged in a matrix M. The details are not so important, so there will be a matrix M in the game, taking values in G mod H, which will encode these various scalar fields which you have in 3 dimensions. And this is coupled to gravity. Now you go down from 3 to 2 on a further isometry. So you write down your 3-dimensional line element in the usual fashion. There is going to be an isometry direction here, which I call phi. And then there are going to be associated to that warp factors. So there's going to be the warp factor in the isometry direction here, which I'm denoting by rho tilde. And then there's a 2-dimensional metric here. Now, in 2 dimensions, you can take this metric to be conformally flat. So there's a warp factor here, psi, that's the conformal warp factor of the metric in 2 dimensions. And here is the flat 2-dimensional metric. It's given in terms of coordinates rho and v. And you may wonder about this lambda there. This lambda takes values plus or minus 1. If lambda is 1, then this means that the 2 coordinates rho and v are space-like. If lambda is minus 1, it means that one of them is time-like. All right. So now you're in 2 dimensions. And so what you have is you have the scalar fields, which are encoded in the matrix M, and they are now functions of rho and v. And you have the warp factors rho tilde and psi, and they're also just functions of rho and v. Now you look at the resulting equations of motion. So you will have equations of motion for the scalar fields encoded in M. You will have one for psi, you will have one for rho tilde. So let's first look at the field equations for the scalar fields encoded in the matrix M. You take M, you take its exterior derivative multiplied by M inverse. So you have this matrix 1, 4 now. So this is a matrix whose components are one forms in rho v. And since this matrix has this Maurer-Cartan form here, the associated field strength is 0, and the equation of motion for M takes this form here. There is a matrix 1 form here. You take its Hodge. Then there is a Hodge star here in 2 dimensions. It operates like so here on the coordinates rho and v. You multiply it with this word factor, rho tilde, you take a further exterior derivative. So there are 2 derivatives in the game here. These are the field equations, and they are rather complicated. Then there is also the field equation for rho tilde, that's just box of rho tilde equals to 0. And then finally, there is also a field equation for psi. Now, you don't have to worry about the field equation for psi, because it turns out that if you solve the field equation for the scalar fields encoded in M, and if you have also solved the box rho tilde equals to 0 solution, so if you have constructed a solution A rho tilde to these equations, then you can show that the equation of motion for psi is integrable. So you can just simply integrate. It uses this as an ingredient, and then you simply integrate it, and you have solved your equation of motion for psi, so you don't have to worry about psi anymore. In the following, I'll just be focusing on these 2 equations. But now things can be further simplified by choosing appropriate coordinates rho v. You see, in 2 dimensions, you can always various rho v coordinate systems will be related to one another by conformal transformations. So you can pick coordinates rho v such that rho tilde, this word factor here, gets identified with rho. So that's what we are going to do now. Yes. Yeah. Yeah. We are assuming that we went from d dimensions, d bigger or equals to 4, down to 3 dimensions. In which case, the fields M would a priori depend on the coordinates in 3 dimensions, but now we assume a further isometry reduced down to 2 dimensions, in which case M will only depend on the coordinates in 2 dimensions. They are what? True, but each of these entries in that matrix will be space-time-dependent fields in 2 dimensions. Will be functions of rho v in 2 dimensions, right? Right. So as I said, so we then simplify these set of equations of motion by picking rho tilde to actually be equals to rho, in which case you don't have to worry about this anymore. This is solved. And so, so having set rho tilde equals to rho, if I go back here, setting rho tilde equals to rho, then this becomes replaced by rho, and these are the field equations you now have to solve. And once again here, once you set rho tilde equals to rho, then what used to be rho tilde here becomes rho. So this is then the passage from the 3-dimensional line element to the 2-dimensional line element, and these are the field equations you want to solve. Now, as I said, this will now be solved by Wiener-Hopf matrix factorization theory, or associated to it matricial Riemann-Hilbert problems, which I'll be introducing shortly. But before I do so, coming back to Abiram's question, what are typical symmetric spaces which arise in these reductions? So here I give you now I will give you 3 examples, simple examples. Suppose you start with the Einstein action in 4 dimensions, just gravity. Then you dimensional reduce down to 2 dimensions. The coset that you get is an SL2R coset. So what is the structure of the matrix M that you get? You start with a 4-dimensional line element. There you reduce it down to 3 dimensions in the first step by along a certain isometry, which I have called Y here. There is going to be a word factor, delta, multiplying this isometry direction, and then there's the 3-dimensional line element here. There is also this metric element B here. So when you go from 4 to 3, you have these two metric elements, delta and B, and they are the ones that get arranged in this matrix M here, which is a 2 by 2 matrix. And then you are in 3 dimensions, and you further reduce down on the isometry direction phi, and this is then what you would be solving in this particular model here. Now you can look at more complicated theories. Suppose then that you want to start with an Einstein-Maxwell theory in 4 dimensions. Then you discover that as you go from 4 to 3 to 2, that the coset space you get will be based on the Lie group SU2, 1. And this means that your matrices M will now be 3 times 3 matrices, whose entries will then depend on rho and V. You could be more ambitious and say add to this Einstein-Maxwell system a dilaton field, in which case you can also repackage this and say, well, this is just includes a Klein reduction of 5-dimensional Einstein gravity, in which case you will be finding a coset based on SL3, R. And again, the matrices are 3 times 3, and you can proceed in this way and look at more and more complicated theories, and you'll discover that the associated cosets that you get, or the representatives M, get bigger and bigger rank. Yeah. Yes.
Delta.
Yeah.
What is the form of delta? That's the form, doesn't work like this.
Yeah. So the form of delta will now be dictated by solving the equation of motion, right? Right. You have one? Well, I will give you later examples. So this is generic. All you have done is you have started with a 4-dimensional action or 4-dimensional equation of motion, reduced them down to 2 dimensions. The resulting 2-dimensional equations are now expressed, are these ones, where A is expressed in terms of M, and now you have to solve them. And now you have to study the space of solutions of these equations here. And there will be all kinds of solutions in that space, right? But we'll see examples of how to actually construct such solutions without actually solving these differential equations, but rather doing matrix factorization theory or solving associated Riemann-Hilbert problems. Yeah.
It's correct that you always start with red signature.
That was my assumption here.
So the lambda is
Correct. Yes. Right. Now, the only thing you now need to know for the remainder of the talk, the only thing you need to know is that these symmetric spaces based on G mod H, they come endowed with an involution that operates at the level of the Lie algebra. You can then use this involution to decompose the Lie algebra of G into the Lie algebra of H and the rest. And so, for instance, now the form of this involution will depend on the cosets on the symmetric space you are looking at. For instance, in this example here, where you have this coset space here, the involution is just transposition. So the involution will then act on the generator, on the Lie algebra generator simply by transposition. And this then gets exponentiated, this then gets further this then becomes at the level of the group, at the group level, the action of this involution is obtained by exponentiation. And the only thing for the rest of the talk that you need to know is that if you now take a representative of this coset, that it's going to be invariant under this involution. As I said, for the specific coset here, involution means transposition. In these other examples, it will be something more complicated. So keep in mind now that there is an involution here, which for the example of Einstein gravity acts as transposition. Now we come to the linear system. So we want to solve these nonlinear partial differential equations in 2 dimensions. And the statement is that this is an integrable system. So what does this mean that it's an integrable system? So according to Eads, and this is the definition we are going to use, an integrable system is the statement that the equations of motion of the system you are looking at are the compatibility conditions for an auxiliary linear system of differential equations. So let me explain these words a little bit here. So what you see here is you see a system of first order differential equations. They're only first order derivative. They're only first derivatives here. So it's this is a system of first order differential equations for an auxiliary object called X. This is a matrix function, but again, its entries depend on rho and V. And what you see here is that there is A here as an input into the system. So A is what you seek. A is what is going to be a solution to the equations of motion. But assuming that you have found the solution to the equations of motion, then you stuff the A in here. And this is going to be your auxiliary system with A as an input. And then there is this tau here. And this tau is called the spectral parameter. Now, I will tell you on the next slide what I mean by compatibility condition. But the point is that to these equations of motion, you associate a linear system or a Lax pair, as we shall see, which has A, the object you want to solve for, the object that determines your solution, that determines a solution to the equation of motion as an input. Now, before telling you what this compatibility condition looks like, let's look at tau. So what is tau? Tau here is a spectral parameter. How is it introduced? It's introduced in the following way. You start with two copies of the complex plane, each of them with a complex coordinate tau, each of them with its complex coordinate tau and w. And in the C2, you impose a relation, which is, well, if you multiply this by tau here, is going to be an algebraic relation between tau and omega. And you can check very quickly, easily, that this relation is invariant and the tau goes to minus lambda divided by tau. Remember, lambda was plus minus 1. It told you whether rho and d were both space-like directions or whether one was time-like and one was space-like. Now, given this relation, there are two things you can do with it.
Where is the relation from?
Right. One way of determining this relation is by studying the compatibility equation for the system, in which case you will be driven to that. Here I'm simply going to postulate it. But the omega, yeah, the omega. Yeah, I'll come to that in a second. So this object here now, there are two ways of looking at it. You can either say that you view omega as a function of tau in the presence of parameters v and rho, which happen to be space-time coordinates, but are parameters nevertheless. Or you can solve this relation for tau as a function of omega, rho, and v. Both points of view play a role. But since I'm currently discussing the linear system, I'm first focusing on the second point of view. So I take this relation. We are then instructed to solve, to view tau as a function of omega and rho v, in which case you get expressions of this sort here. And the way to think about this is to say that you have now defined a function of rho v, which will depend on the parameter omega, which is complex, but it's a parameter. And you're instructed to use one of these members. So this defines for you a family of functions indexed by an omega. You take an element of this family, you stuff it in there. So this tau gets replaced by this object. You stuff it in there. And now everything in here is a function of rho v in the presence of a parameter omega. If you have an input A, then you plug it in there, and now you solve for X, and the resulting X will then of course be a matrix whose elements will depend, whose entries will depend on rho v, but also on this parameter W. All right. So that's one point of view. The other point of view, where you take omega and you view it as a function of tau in the presence of parameters rho and v, that will come later. So suppose you have done that. So suppose that you take a given solution of the equations of motion, you put it in here, you select one of these members of this family, put it in there, you solve for x, well, then you'll get an x that depends on the space-time coordinates rho v as well as on the parameter w. Now, what is the meaning of that? Here is one thing you can do with it. Using this x, this is the x associated with a given solution A, you can now construct an infinite set. Well, you can now construct a set of conserved currents, and it's going to be an infinite set. And the fact that you have infinitely many conserved currents is the hallmark of integrability. So you take this Nicolai current, defined as follows. You take this x, which depends on w, you differentiate with respect to w, multiply with the x inverse, take the exterior derivative, take the hot star, and this will then define for you, this will be a generating function of currents, of conserved currents, and which you can extract by taking this one form, by taking this matrix one form J, expanding in inverse powers of W, and its expansion coefficients will give rise to infinitely many currents J of rho v. So yeah.
Can I ask you, I'm happy to believe it, but this is if there's some intuition behind why this current is a good current to write down, where it comes from.
There is some intuition in Nicolai's paper, indeed. This defines for you what is called Kac-Moody currents. Right. I have to, well, I guess I will have to refer you to the paper by Nicolai for a better understanding of how this current arose.
But I think,
fair enough.
I think more thing should be a part of if you would do it in any quadratic of design algebra, which isn't a fine extension either. So I think you get a fine extension of what should I easily get as a fine dimension. Also has something to do with that in two different combinations for the infrarossum entities, you find SU2 algebras which don't commute with each other, but whose interplay then generate something infinite dimension. You think Kac-Moody algebras that you would be aware of this effect. So this sort of thing in SU2 algebra, which is the power of both, that one level up and just enough to create infinite dimensional algebra because you go up in that stating up.
What is certainly interesting, or the thing to notice, is that in the construction of these infinite many currents of Nicolai, that the W plays a role. You take the you differentiate with respect to W, so this plays a crucial role here in constructing these currents. So right, okay. So this is the comment I'm going to make. But now, so this was to address what one of the consequences of the linear system is, namely the fact that you have that you can construct infinitely many conserved currents by using the X that arises as a solution to the linear system with A as an input. But now coming back to the statement here, what do I mean by when I said that this linear system here was a compatibility condition? Sorry, that these equations of motion were the compatibility equation for this linear system. What do I mean by that? So here's what I mean by that. So this is a linear system. Remember that tau is replaced by one member of this family. Now, remember that A is a matrix 1 form, so it will have two legs, A row and AV, but A row and AV are both matrices. And now this is called a linear system. It's linear in X, but it's also called a Lax pair. So now let's turn this into a pair. Let's make the pair explicit. So, for instance, look at the left-hand side here. As I said, A has two legs. Suppose you look at the D row leg here. Then this side here will go like so. Over here, you will have to look at the DV leg of DX, whose star is D row, so you get that. So by looking at the D row leg of this expression, you are driven to this differential operator L. And likewise, by looking at the dv leg of this expression, you're driven to the differential operator M. And then this statement here, the statement that you want to solve this linear system with A as an input, becomes equivalent to taking these differential operators, letting them act on X and setting them to 0.
It's not the same M and G1.
Oh, sorry. Yeah, you're right. It's a different M. That's terrible notation. Right. I forgot to change notation. I'm terribly sorry for that. Right. So this is now really terrible, isn't it? Right. Thank you. Yeah. This should have been calligraphic L and calligraphic M to separate them from the cosset representative M. Thanks very much. Yeah, indeed. Sorry for that. So then you do that. And of course, a consequence of that is that the commutator of L and M has to be 0. So that's now your compatibility condition. The commutator has to be 0. You evaluate it and you discover that whereas L and M are differential operators, by the time you evaluate this object here, this is not a differential. But by the time you evaluate that, you get a matrix expression and acting on X, not any longer a differential operator acting on X. Now let's assume that X, the solution to the linear system, is invertible. So you hit this with X inverse, you peel off the X, in which case the bracket here has to vanish. But the bracket comes with different powers of that function phi. And so from here you conclude that the individual terms have to vanish. So this term has to vanish and that term has to vanish. Now, this is precisely the equation of motion, which you want to solve. And this is simply the statement that A is a flat connection. So indeed, the compatibility condition for this Lax pair implies the equations of motion. And this then explains what I told you here, that the equations of motion are the compatibility equation for the Lax pair. Now we would like to solve this. So now here, now. So I just said, right. So now here's the linear system again. And as I said, if you have a solution A to the equations of motion, then if you stuff it in here, you can construct the associated X. But the purpose of this was to construct solutions to the equations of motion. So this linear system here is nice, but it uses A as an input, but A is a solution to the equation of motion, which is precisely what you are trying to get at. So the way to actually look at this linear system is to say that there's a pair of unknowns here, namely A and X. A is going to be a solution to the equation of motion. That's the thing you are trying to solve for. Once you have a solution for A, then you can construct the associated X by solving this equation for that A. So once again, the way to look at the linear system is actually to say that there's a pair of unknown here, A of X. So how are you going to solve this? Well, the statement is that you can now determine the pair A of X in one shot by performing what is called canonical Wiener-Hopf factorization of a monodromy matrix with respect to a certain contour, gamma. This I will have to explain. And this in turn is nothing or is equivalent to a factorization problem. Sorry, this factorization problem is equivalent to a particular Riemann-Hilbert problem. And that's what I'm going to explain next. So this Riemann-Hilbert problem, which will be based on a matrix, will, at the end of the day, provide you with a pair A of X, where A is going to solve the equation of motion, and X, the resulting X, will be a solution to the linear system with that A as an input. It's going to come out in one shot. But now I have to explain all these words here. So first of all, what is a Riemann-Hilbert problem? Now, there are all kinds of Riemann-Hilbert problems. We'll be interested in a specific matrix or matricial Riemann-Hilbert problem. This Riemann-Hilbert problem will be associated with the factorization of a monodromy matrix with respect to a contour in the complex tau plane. So first we have to pick a contour. So here's a contour in the complex tau plane. It's going to be a closed contour encircling the origin. It's going to be a simple contour. And of course, what this contour does is it separates the complex plane into two regions, the inner region, which I'm going to denote by D plus, and the outer region, which I'm going to denote by D minus. Now, what is a Riemann-Hilbert? What is a matricial Riemann-Hilbert problem? This is a statement that you seek a matrix phi that is going to be analytic in the region outside of the curve. It's going to be analytic in the region inside of the curve. And on the curve, there will be a jump condition. So let me be a bit more precise. So you seek a matrix function phi, which is going to be analytic in the outside and in the interior region. Let's denote the matrix that is analytic inside the curve by phi plus. Let's denote the matrix that is analytic outside of the curve by phi minus. And on the curve, you demand that if you take phi plus defined in the interior and analytic in the interior, if you take phi minus defined in the exterior and analytic in the interior, you now look at their limiting values as you approach the curve in a non-tangential manner. Let's denote these limiting values again by phi minus and phi plus. Then you want these values to be related by a jump condition encoded here specified here by this matrix G. So once again, you want to construct a matrix phi that is analytic in the exterior, analytic in the interior, and on the curve, as you take the limiting values of the matrix in the exterior to the curve and of the matrix in the interior to the curve, on the curve, the resulting matrices satisfy a jump condition. That's a matricial Riemann-Hilbert problem, and there is no general procedure for solving these things. So this has to be done on a case-by-case basis. Now we'll be looking at a very specific matrix Riemann-Hilbert problem called the Wiener-Hopf factorization problem. So here it is again, in a nutshell. We are on the complex tau plane. We are on a complex tau plane. We are given a contour in the complex tau plane. And we are given a matrix curly M on this contour. We'll be assuming that this matrix is invertible and that both M and the inverse are continuous on the contour. And now what we seek is a matrix M plus defined in the interior, a matrix M minus defined in the exterior, such that M plus is analytic and bounded in the interior, and so is its inverse. M minus is analytic and bounded in the exterior, and so is its inverse. And as I take M plus and M minus, so M plus is defined in the interior, analytic, bounded, M minus is defined in the exterior, analytic and bounded, and now I take the limiting values to the curve, gamma. On the curve, M plus and M minus are going to be related in this manner here. So I gave you a curve gamma with a matrix curly M defined on gamma. And what we seek are matrices M minus and M plus, such that on the curve, This matrix M, which I gave you, and which was continuous on the curve, has this decomposition into an M minus, which is analytic and bounded in the exterior, and so it's inverse. An M plus, which is analytic and bounded in the interior, and so is its inverse, and a diagonal matrix D that has diagonal entries given by powers of tau, such that the sum of these powers adds up to 0. That's Wiener-Hopf factorization for you. So once again, I give you a matrix M on the curve gamma, such that M and M inverse are continuous, and I seek a decomposition like so in terms of 3 factors with these properties. Right.
I think I might have gotten confused. So the purpose of all this is to solve a differential equation, right?
Right.
And I think that you said that the solution of that equation depends on the curve gamma that you take.
That's right.
But so it's a second order differential equation. So
Yes.
there's 2 solutions. So but there are many gammas you can draw. So
Right. So I haven't. Right. So right. Right. So things will depend on the choice on gamma, but they will of course also depend on the choice of M. So what you do is you choose an M and a gamma, and what you will discover is a particular solution. If you now decide to choose a different M or a different gamma, you will find some other solution to the equations of motion.
yeah.
Then you will continue. You will continue. Well, when I say that you will be finding a solution to the equation of motion, I mean to say that this will be so if this Wiener-Hopf factorization I'm looking at here is a so-called canonical one. I haven't introduced canonical one yet, but so long as you are dealing with canonical Wiener-Hopf factorizations, then any choice of M which you pick, any choice of this matrix M which you pick, and associated to that a contour which you may have in your setting, that will give you a solution. Yeah. But they may be very distinct. They may be distinct. Yeah. Well, they will be distinct in general.
So you have maybe a family of solutions, and we're finding numbers of
That is true. Yeah. That can also happen. Yeah.
Right.
But I'll give you examples later. So at the moment, I'm just introducing theory, and then in 8 pages or so, I'll give you a bunch of examples.
Okay.
All right. So again, I'll give you an invertible matrix M on the contour. I demand that it's continuous, and so is its inverse, and then I seek a decomposition like so. Now, there is this diagonal matrix appearing here in the middle. Let's suppose, and the condition is that the sum of these exponents adds up to 0. Now, when all the exponents of this diagonal matrix are 0, so in other words, when the diagonal matrix is the identity matrix, then you call this a canonical Wiener-Hopf factorization, and it's these ones which we'll be focusing on. But there are 2 obvious questions here, which is, when is it that a given matrix M that is continuous on the curve gamma, which you have chosen, when is it that it actually admits such a Wiener-Hopf factorization? That's one question you may ask. And there's a theorem here, which from the 80s, which says that if the entries of the matrix M that you picked are not just continuous, but actually Hölder continuous functions with a certain exponent between 0 and 1, then for any such matrix defined on the contour whose entries are functions of rho v that are Hölder continuous, then rho v is irrelevant. I just misspoke. So sorry. We are here on the complex tau plane. So whenever we have a function curly M, whose defined on the contour gamma, whose entries are Hölder continuous functions with exponents in the range 0 and 1, then such a matrix admits a Wiener-Hopf factorization. Now, we'll be interested in canonical Wiener-Hopf factorizations, which are a special case of Wiener-Hopf factorization. So you may ask the same thing about canonical Wiener-Hopf factorizations. And their things are even more complicated. So there is this theorem here, which says that if M, the matrix I give you on the contour, is a triangular matrix, then it will have a canonical factorization if the diagonal elements admit a canonical factorization. All right, so that's the theorem you have at the moment. So I'll come back to that theorem later. But now let me proceed. So suppose you have picked a matrix M that has a matrix M defined on the contour gamma that has a canonical factorization. Then it means that it can be decomposed into a product M minus and M plus on the contour. And this decomposition is actually unique up to a constant matrix, and you can use that constant matrix to impose a normalization condition. And if you do so, then you then one way of picking a normalization condition is to say the following. So curly M is the matrix I give you, defined on the contour gamma. M minus is a matrix that is analytic and outside, in the exterior of gamma. M plus is going to be a matrix that is analytic and bounded in the interior of gamma, and these are the limiting values of M minus and M plus as I approach gamma in a non-tangential way. Now, M plus is a matrix that is bound analytic in the interior of gamma, so it's bound and analytic at tau equals to 0. So you pick a normalization where you say that M plus at the origin is the identity matrix. And that's for you a canonical factorization of M, assuming that M has a canonical factorization. Now remember, the goal was to obtain a pair, an A that solves the equation of motion and an X that solves the associated linear system. So how is that related to what I just told you here? Coming back also to your question. So the relation is that. So what is the relation? So you have to pick a starting point, which means that you have to choose a matrix curly M on the contour gamma. How are you going to do that? Well, you start from a matrix curly M that depends on W. You take it to be determinant M you take it to be a matrix with determinant 1 with determinant equals to 1. You take it to be a matrix that is invariant under the involution I had introduced earlier on. Now remember, there was a spectral curve relation, and this is the other point of view. You now view omega as a function of tau. So you substitute omega by this relation. And now you're dealing with a matrix M that depends on tau. And rho and V are simply spectators, they are parameters. So that's what this notation is indicating here. So now you have a matrix defined on the complex tau plane, which you are going to canonically factorize with respect to a contour gamma. But remember that this relation here was invariant under tau goes to minus lambda divided by tau. What this means is that the contour gamma you are going to choose will be invariant under tau goes to minus lambda divided by tau. Now, this involution here has fixed points. So if lambda is 1, the fixed points are at plus minus I. If lambda is minus 1, they are at plus minus 1. Remember, lambda told you whether rho and v were space-like or one of them was time-like. So the curve, therefore, since it's invariant, since it's chosen to be invariant under this, will have to pass through the fixed points. And that's what you see in these pictures here. The fixed points at 1 minus 1, the fixed points at I minus I. Now, let's also pick a region O that around the curve, which will demand to be invariant under tau goes to minus lambda tau. So that's what you do. You pick such a matrix, curly M of W. The choice is yours. You do that substitution. You pick a contour that has these properties. Then you find the following. So this matrix M will now actually, this matrix M will take it now to be analytic in this region O. We'll take it to be analytic, we'll take it to be analytic in this region O, and we'll also demand its inverse analytic in its region O. We'll now assume that it has a canonical factorization with respect to the chosen contour. So it means that where recall that this factor is satisfies the normalization condition at tau equals to 0. This factor was bounded and analytic in the interior, satisfies that normalization condition. Now take M minus. That's the factors analytic and bounded outside. It's bounded and analytic at tau equals infinity. Compute it at tau equals infinity, and you get the matrix M of rho v. That's the matrix that solves the equations of motion. So that's the theorem you have. You have done the canonical factorization of this matrix curly M of W. You assume that this was analytic in that region O that includes the contour gamma, and also its inverse was analytic there. And then there's a theorem which says that that the M that you get by taking the M minus and evaluating at tau equals infinity, that is the solution to the equation of motion. And the solution to the associated Lux pair is the M plus, this M plus, where tau is substituted by this function phi of W belonging to that family which I had introduced earlier on. So in other words, the canonical factorization gives you the A or the M, the matrix M that solves the equation of motion coming from M minus, and it gives you the X that is the associated solution to the linear system coming from M plus. And this is an extremely neat and powerful thing. Now, this is a theorem, and this was only proved recently, and the way this was proved is actually by realizing that there is a second Riemann-Hilbert problem in the game. Now, just a few words about the second Riemann-Hilbert problem, because it will play a role in a second. So to prove this, there's a second Riemann-Hilbert problem in the game. And this second Riemann-Hilbert problem arises as follows. Take this matrix curly M, which you picked. Remember, it came from curly M of W by substituting W in this manner. What does that mean? It means that if you take this curly M and you substitute tau back, and you replace, well, and you substitute tau by this function phi of W, then you are back to your matrix curly M of W, which is independent of coordinates rho v. So the exterior derivative with respect to rho v vanishes. So this is a state, so you have a vanishing everywhere in this region O that includes the curve. Now, so this is the exterior derivative of this matrix curly M of W. Now you can massage this, and what you realize is that this expression becomes a statement about two analytic functions, f plus and f minus, f plus analytic and bounded in the interior of the curve, f minus analytic and bounded in the exterior of the curve, and on the curve, they have to be equal. Now, this is a Liouville problem. It therefore tells you that you have an analytic function f, and therefore f plus equals f minus on the curve tells you that they have to be equals to a constant, and using this, you prove that theorem. Now, this is very, how shall I say, it's just a comment, but this comment will play a role in the following. But before I get there, let me just make another statement. So you picked a curly M of W, which here it was. You picked a oops, where was it? You picked a curly M of W. You substituted W by this expression, so now you have an M of rho v tau. And if this has a canonical factorization, then you say that this is the monodromy matrix for the solution M of rho v. Now, coming back to Victoria's question, this M of rho v was obtained by canonically factorizing this matrix with respect to a certain contour. If you now decide to change the contour, say you pick another contour that is not homotopically equivalent with respect to the first contour you picked, then you may, and if you then again perform the canonical factorization with respect to this new contour, you will find a different solution, M of rho v. So the same matrix can give rise to several solutions to the equation of motion. Now, a final comment. I had told you that this curly M of W was chosen such that it was invariant under the involution. There is a nice consequence of that. If you work out what this means, it means the following. It means that the M minus factor here can actually be re-expressed in terms of the M plus factor and in terms of M of rho v in this manner here. And this is now a very neat formula. It means that the matrix M defined on the curve gamma, the one that you canonically factorized, if there's a canonical factorization, it can be written in this manner. And this is beautiful because in one shot, you see that there is the matrix M of rho v here that solves the equation of motion. And this one here solves the associated Lux pair. Now, let's proceed. So this was about canonical factorization. Now you may wonder, what if I decide to go away from canonical factorization? Are there situations in which by going away from canonical factorization, I still get an equation of, I still get a solution to the equation of motion? And the answer is yes. And the way we discover this, or the way, or a systematic way for going away from a canonical factorization, while still ensuring that the factors you get will give rise to a solution to the equation of motion, that came out of this proof, which told you that a canonical factorization gives rise to a solution to the equation of motion. And this came out as follows. If you carefully look at the proof, which told you that a canonical factorization gives rise to an equation of motion, you will discover that the M plus factor, that what is crucial in that proof is that the M plus factor, which in the canonical factorization was taken to be analytic and bounded in the interior of the curve gamma, actually, you discover that all there is required is that M plus and its inverse are analytic in the vicinity O of the curve, but M plus need not necessarily be analytic in the interior of the curve gamma. So that means that so long as you have factors M plus that are analytic in that neighborhood O of gamma, but not necessarily in the interior, and so long as you satisfy a generalized Riemann-Hilbert problem, you may actually have a generalization. You may actually be able to go beyond canonical factorization. And this we called multiplicative deformation of canonical factorization. So let me briefly describe that, and you will hear more about that in the talk by Kasner camera at the workshop. So what do I mean by all these words now? So let's have a look at an explicit example. Let me briefly describe that. And then in the remaining 20 minutes, I'll give you lots of examples, concrete examples of solutions that are generated in this manner. Suppose I take the identity matrix. Now, if I were to canonically factorize the identity matrix with respect to a contour, I would find, so canonically factorizing a matrix means that I get a decomposition like so. And that means that I would get a decomposition in terms of three matrices, all of them the identity. Totally uninteresting. But now suppose that I decide to take the identity matrix and I'm able to write it as a product of these factors here, which mimics what you see here. But it's just that I require anymore R to be analytic and bounded in the interior. R will have to be analytic and bounded in the region O, but not necessarily in the interior. Oops. And then there is another matrix N here such that this product here gives the identity matrix. Then I can do the following. Suppose I start from a matrix curly M that has a canonical factorization. So here's a canonical factorization. Now I insert the identity in there. I just insert it there. So then what happens? This R goes together with n plus. That's what you see here. Then I have this M. Then I have this R natural times N there next to M. Let me assume that R commutes with M. So I can then pass this R to there. And then I have this expression here. So then I have now a different decomposition of my original monodromy matrix into three factors, where this one is not analytic anymore in the interior of the curve gamma, because R was not any longer analytic in the interior. And so the question is, this middle factor, is this, so I have another decomposition of my monodromy matrix in terms of factors that in terms of products of matrices that have that reflect that structure, but such that this one is not analytic anymore in the interior. Question, is this middle factor a solution to the equation of motion? And you can prove a theorem stating that yes, it is a solution to the equation of motion. So what we have done here is as follows. We have started from a monodromy matrix that has a canonical factorization. And then we have deformed the canonical factorization, the M plus, by multiplying it with a function R that was analytic in the vicinity of the curve gamma, but not necessarily in the interior. We call this a multiplicative deformation of the canonical factorization. And the resulting factor, one can prove this, is again a solution to the equation of motion. So what is an example of that? Kasner solutions. Cosmological Kasner solutions cannot be obtained by canonically factorizing monodromy matrices, but they can be obtained by a multiplicative deformation of the canonical of a canonical factorization. Now, this is just an example. If you take R, the matrix R that appeared here to have a simple pole in the interior, declared given here by tau 0, and you pick the function M that only depended on rho v to be given by this expression, the details are irrelevant, you find that the multiplicative deformation, you find that if you start from a certain monodromy matrix that has a canonical factorization, and you then multiply it with this R, you find that the associated matrix here solves the equation of motion and describes a cosmological Kasner solution. I'm not going to give you the details of this, but this is just to illustrate that indeed you can get interesting classes of solutions to the equations of motion by moving away from canonical factorization in a very specific manner. All right. So now I have 20 minutes, and now I'm going to give you a bunch of examples. Before I do that, let me go back to the question as to when is it that a matrix defined on the contour has a canonical factorization. I told you earlier that there was a theorem which said that if the matrix is triangular, then it will have a canonical factorization, provided the diagonal entries have a canonical factorization. That was a generic statement. Let's sharpen this a little bit. Suppose I give you a matrix curly M defined on the contour that is diagonal. I can look at each of these diagonal entries. If these diagonal entries are continuous and non-vanishing on gamma, then you can actually prove that each of these factors in the diagonal matrix has a canonical factorization. And this has to do with the very special property of the spectral curve relation. So therefore, what this means is that you have this theorem. Previously, I told you that whenever we are dealing with triangular matrices, well, they will have a canonical factorization if the diagonal entries have a canonical factorization. This theorem tells you that the diagonal entries will have a canonical factorization so long as these entries are continuous and non-vanishing on the curve gamma. So that means that any triangular matrix, and therefore any diagonal matrix, such that the factors in that matrix are continuous and non-vanishing, such matrices all have canonical factorizations. All right. So here you have a class of matrices for which you are guaranteed to have, which are guaranteed to have a canonical factorization. So now let's look at explicit examples. Let's start with diagonal monodromy matrices. Now, it turns out that diagonal monodromy matrices can always be explicitly factorized, either by invoking Cauchy type integrals or generalizations thereof given by these Sokotsky-Flamel formulae, or by using simple complex analytic tools. So let me explain that now. In the first example, let's pick a diagonal matrix, and so we pick an M of W, and let's pick it to be rational, like so. M here is a parameter which we take to be positive. It has determinant 1, and remember that, here we are in the context of Einstein gravity, reduced from 4 dimensions down to 2. The matrices are 2 times 2. The generalized transposition is the involution is just transposition, and so this matrix satisfies that. Now replace omega by its spectral curve relation. You may remember that omega was something like tau squared plus blah 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 divided by tau. So in other words, replace omega by tau by the spectral curve relation, in which case you get functions of tau that are rational. So replace omega by an expression that involves tau squared. What you're going to get is an f of tau that is a rational function in tau, and the numerator and the denominator are quadratic in tau. And this function f of tau will have zeros and poles given by these expressions here. Now, for concreteness, let me take the case where lambda is 1. Lambda equals 1 means that both rho and v are space-like, for concreteness. Now, this is what you would like to factorize. So you can factorize, you want to canonically, so now you will now pick a contour gamma, and then canonically factorize this with respect to that contour gamma. Now, we picked lambda equals to 1. That means that the contour has to pass through the fixed points plus minus I. And it turns out that there are 4 possible inequivalent choices of contours you can pick. Why is that? You see, this function f of tau here can have zeros and poles at locations tau 1, tau 2. You don't want these poles to be on the contour. So there are 2 zeros or 2 poles called here tau 1, tau 2. And therefore, you have the following 4 possible choices. Either tau 1 and tau 2 are both inside the contour, or they are both outside the contour, or one of them is inside the contour and the other one, or the other one is inside the contour. That gives you 4 choices of contours to look at. Pick one of such choice, do your factorization. What you will find is that you will get 4 distinct classes of solutions, all coming out of one and the same monodromy matrix. So for instance, let's pick this case here where tau 1 and tau 2 are inside the contour. So now the zeros, well, oops. So let's see. So now tau 1 and tau 2 are inside of the contour. You want to factorize f into a product, f minus and f plus, such that f minus is analytic and bounded outside, and so it's inverse, and f plus is analytic and bounded inside, and so it's inverse. How do you do that? So here is the f. As I said, you want to factorize it into an f, m minus and an m plus. The m minus has to be analytic and bounded outside, and so its inverse also has to be analytic and bounded inside. Now we took tau 1 and tau 2 who lie inside of the contour. So that means that out of these 4 factors you see here, you pick these 2, and they will comprise the m minus. Why? Because tau 1 and tau 2 are inside the contour, So therefore, therefore M minus doesn't have poles. M minus, which has to be analytic and bounded outside, doesn't have poles there because tau 1 and tau 2 are in the inside, and its inverse also doesn't have poles. So that's what you pick for M minus, and the rest will be M plus. So the other two factors will be M plus. But now remember that M plus had to be normalized at tau equals to 0. So that means that you have to multiply this by this factor here and divide by here. So that's your canonical factorization, something you do in 2 seconds. Now you take M minus, and you are instructed to evaluate it at tau equals infinity, and that will give this here as your entry in M rho V, and you do the same thing for this one here. And so in one go, you have constructed an M of rho V that satisfies your equations of motion. Now you can look at the space-time meaning of that, and you find it's the exterior region of the Schwarzschild black hole. But you could have done exactly the same thing with respect to any of these other 3 contours, in which case you discover that putting it all together, 4 contours, 4 different solutions, what you discover is that you end up generating the entire class of A metrics, which is a terminology used in Griffiths and Podolsky. And it's all coming out of one and the same monodromy matrix.
For the non-experts, what are the A metrics?
These are going to be exterior of Schwarzschild solutions, hyperbolic versions, naked singularities, and things like that. So take your Schwarzschild solution. It has its line element has a 2-sphere part there. Change the sign into a hyperbolic sign. That will be part of it, and things like that.
But at the moment, that's coincidence, right? Coming out, or is this
that you get precisely the entire A class, that is something that's done by observation, that you expect to get all kinds of different solutions. That is sort of clear because these contours are not homotopically equivalent, but that you get the A class, well, I don't have. You could perhaps say, well, perhaps you have to get it because this only depends on one parameter M, and the A class also only depends on one parameter M. No, I'm not sure this is a very convincing argument. All right, so that was the simplest monodromy matrix you could pick. Let's complicate things. So here is now a diagonal matrix that is non-rational and has essential singularities, given like so. And this is a matrix that was analyzed recently by Robert Penna, who will also be at the workshop. So here you have that thing. This looks, so now again, translate omega into tau using the spectral curve relation, and you will see, well, that this has essential singularities at tau equals infinity and tau equals 0. But it doesn't have any other singularities in the tau plane. So you're looking at the punctured tau plane. Therefore, any contour in the punctured tau plane will be homotopic to any other contour in the tau plane. So here you just have one contour at your disposal. Now, how do you factorize this? Well, there is a theorem well known in factorization theory, which says the following. Let's look at one diagonal entry, this one here. It's the exponential of this function f of tau. This function f of tau is continuous, and it's actually Hurler continuous on the contour gamma. Since it's Hurler continuous, it's known that it has a unique decomposition into 2 factors called P plus and P minus, where P plus and minus are projectors. And what are these factors? These factors are the limiting values of the following. There is going to be a function that is analytic and bounded in the interior of the contour, call it P plus F. There's going to be a function that is analytic and bounded in the exterior of the contour, call it P minus, and on top, this function vanishes at tau equals infinity. If you then take these functions and you look at its limiting behaviors as you approach the contour, that you then get to this unique decomposition. Now, what are these functions? Well, I just told you that we are on the punctured complex plane. There's a singularity at tau equals 0, at tau equals infinity. There are no further singularities. So each in the punctured complex tau plane, any choice of contour will be homotopic to any other one. So let's pick the contour to be a unit circle. If you pick it to be a unit circle, then these objects here are given in terms of Cauchy integrals. If you then, so this one here is defined for tau in the interior. This one here is defined for tau in the exterior of the contour. And if you then take tau to approach the contour, then these formulae become defined in terms of the Sokotsky-Plemal formulae. All right, that's what you have. So you have this decomposition. So m plus will be given by the exponential of p plus, m minus will be given by the exponential of p minus. Remember that you have to normalize things. Now, let's look at p minus. Let's look at m minus. That's the one that will give rise to the space-time solution. M minus is the exponential of p minus times the normalization factor. P minus at tau equals infinity vanishes. So you're just left with the normalization factor. The normalization factor is given by p plus at tau equals to 0. So put tau equals to 0. And this is then what will give, so the exponential of this expression here is what will give rise to m minus at tau equals infinity. This expression is a Bessel integral. So exponentiating it, you find that the space-time solution is given by the exponential of this Bessel function. And this is then, it's the space-time interpretation of that is an Einstein-Rosen wave solution in general relativity. And this was first, this was first analyzed by Robert Piana, but using a different approach from this one here. Let's complicate things. Let's continue complicating things a little bit. Again, let's look at the diagonal matrix. But again, we pick it to be non-rational and to have essential singularities. Again, you may find this is hopeless to factorize, but it can be factorized explicitly. And what you then get here in this case is a superposition of infinitely many Einstein-Rosen waves, which is also called a gravitational pulse wave. So that comes out of here. Now let's look, this was about canonical factorization. I have 7 minutes. This was about canonical factorization. Now let's go over to multiplicative deformation of canonical factorizations to say Kasner solutions. So now let's pick a diagonal matrix that is given like so. This is now a meromorphic matrix. Now let's pick lambda to be -1 because that's what we need for a Kasner type interpretation. This matrix has a canonical factorization and you get something like that. It may not mean anything to you. It's what it is. It describes a certain space-time solution. But now remember that we can deform the solutions that we get from canonical factorization by this multiplicative by this multiplicative recipe which I had introduced earlier on. So now take whatever canonical take the canonical factorization solution I gave you earlier. Now go from the m plus to r times m plus, where r is given like so. And as I said, what you find is that this monodromy matrix, when factorized in this multiplicative deformation way, it will produce a cosmological custom solution. Now, this was all about diagonal matrices. Now, you can also ask, what about non-diagonal matrices? So here I have an example. Well, I call it triangular monodromy matrix, but it's actually a mirrored. It's not really a triangular matrix. It's mirrored. Here's an example of a 3 times 3 matrix. This would be an example that pertains to Einstein-Maxwell dilaton theory. It's given in terms of 2 functions, h1 and h2 of omega. Replace omega by your spectral curve relation. Factorizes, canonically factorizes. Now, if there is this quantity j here, if j is 0, you get the solution, space-time solution you find is an extremely Heisenberg solution supported by a constant dilaton. But if you take j, this ratio, to be different from 0, then you actually find a space-time solution with 2 Killing horizons. and it appears to asymptotically approach a knot space-time. And as far as we could see, the solution is new in the literature. On one hand, on the other hand, it's somewhat reminiscent of a solution constructed by Brill in the 60s, but in the Einstein-Maxwell context, whereas here we are in the Einstein-Maxwell-Dilaton context. So all of this to say that you can also construct new solutions and not just reproduce old solutions in the literature. 4 minutes. So this talk was based on is essentially based on canonical factorizations of monodromy matrices. So the obvious question, therefore, is the starting point of that is the choice of the monodromy matrix. How do you go about in choosing it? Well, it's up to you to choose it. It's up to you to choose a matrix curvy MLW, which you then try to canonically factorize. First, of course, you have to see whether it has a canonical factorization, and if it does have one, then you actually have to do it explicitly. That may not be so able. But if you do that, then you will have generated a solution to the field equations, and this could very well be a new solution, okay? Now, if you now look at diagonal monodromy matrices, say you have two diagonal monodromy matrices, say that you have managed to factorize them with respect to the same contour, then what you discover, or you can prove, is that also the product of these two solutions will be a solution to the field equations. That's non-trivial because the field equations are non-linear, but this is an outcome of this factorization analysis. As I told you, and most of the talk was based on canonical factorization, but you also would like to go beyond that, away from it, because there are, well, because it's a natural thing to ask, and also because in practice you observe that there are interesting solutions, such as Marshall-Kasner solutions, that cannot be obtained from canonical factorization. And one way of going away from canonical factorization is by multiplicative deformation. You start from a canonical factorization, you insert a 1 in this manner here, where R is not necessarily analytic in the interior of the curve gamma, and in this way you get new solutions to the equations of motion from solutions to that arose by canonical factorization. At that stage, you can ask a question. Okay, so all of this somehow depends on having a canonical factorization. What happens if there is no canonical factorization? Now, this can happen, and this will be the subject of the workshop talk by Kshina Kamera. So she will be addressing this question, and what can, for instance, happen is that that on certain lines, on certain curves in your rho V space-time, that you find that there is no canonical factorization. And you may wonder what the interpretation of that is. And in Kshina's talk, you will hear that this is related to the appearance of an ergosphere in rotating geometries. And finally, coming back to what I said initially here, as I said, you may now be interested in deforming your original Lagrangian by turning on cosmological constants, flux potentials, and you may wonder whether you can get a hint as to whether the system remains integrable by using machine learning, and all of this will then be discussed in the talk by Damian Payne. And I stop here.